In this video, we're going to take a look at how to find the nth root of a real number, like a square root, cube root, fourth root, fifth root, things of that nature. And as with most everything in mathematics, it starts with a definition that we use throughout. So the nth root of a real number, the definition is an nth root of a real number b is a solution of the equation x to the n equals b. Now n has to be an integer and it has to be greater than or equal to 2. So like x squared equals b, x cubed equals b, x to the 10th equals b. So n is what type of root you want to take, and b is the number you want to take the root of. Okay, so just a few examples to kind of make you realize what exactly n is here. So like a second root, which we call a square root, of some number b would be any solution of the equation x squared equals that number b. Or a cube root, or a third root, of some number b would be any solution of the equation x cubed equals b. So b is the number we want to take the cube root of, and 3 lets us know that it's a cube root. And then a fourth root of some number b would be any solution of the equation x to the fourth equals b. And then that you can do that for any integer greater than or equal to 2. So let's see what we're talking about here. So the directions tell us to find the real roots, which we know are called solutions to polynomial equations. So we want to find the real solutions to the following equations. So if you have x squared minus 25, oh wait, let's try that again, x squared equals 25, and we're supposed to solve that, we could move 25 to the left-hand side, which is the difference of two squares. So we get x plus 5, x minus 5. And then we use the zero product property. So x plus 5 has to equal 0, or x minus 5 has to equal 0. And we get x equals negative 5, or x equals 5. So we got two solutions. Now, we learned how to solve equations like this back in earlier, when we learned how to solve polynomial equations. But this takes on some new meaning, because we had x squared equals 25. This right here is our n from our definition we just saw. And then this right here, 25, that's our b from the definition we just saw. So we have x to the n equals b. So negative 5 and positive 5 take on some new meaning for this equation. So this tells us there are two square roots of 25. They are negative 5 and positive 5. So this equation had two solutions, negative 5 and positive 5. So negative 5 and positive 5 are the square roots of 25, because those are the solutions we got to that equation. And that's exactly what the definition of an nth root said, is any solution of the equation x to the n equals b. Those are the nth roots of b. So we just found the square roots of 25, and there are two of them, negative 5 and positive 5. Well, let's look at this next one. X cubed equals 8. To solve this one, remember, we only want the real roots. And basically what this equation is asking us to do is figure out what numbers cubed equal 8. Well, there's only one real number that when you cube it equals 8, and that's 2. So x equals 2 is the only real number that when cubed is 8. So there's only one real number that when you cube it, you end up with 8. So that's the only real solution to that equation. Now again, we have this is our, and this is our b. So this particular equation tells us something. So this tells us that there is one real cube root of 8 and it is positive 2. So the cube root of 8, there's only one real cube root of 8 and it's positive 2. So let's try another one. X to the 4th equals 81. Well, we have x to the 4th and we have 81. So x to the 4th can be written as x squared squared, and 81 can be written as 9 squared. So if I move 81 to the left-hand side, I have the difference of two squares. So I end up with x squared minus 9 and x squared plus 9. And then I have the difference of two squares again, so I get x plus 3, x minus 3. And then I have the sum of two squares, which we should know doesn't factor. I'm not using integers. And we can use the zero product property, and we get x equals negative 3. We also get x equals positive 3. And then x squared plus 9, when I set that equal to 0, if I move 9 to the other side, I get some number squared equals negative 9. Well, we know from our study of negative numbers that when you square any number, any real number, it doesn't come out to be negative. So any real number, when you square it, does not come out to be negative. So this has no real solutions. So what I now see, since I had x to the 4th equals 81, remember this is our n, and then this is our b from our definition. So this equation is basically having us find the 4th roots of 81. Well, we got two solutions, negative 3 and positive 3. So both of those are 4th roots of 81. And then this other one, x squared plus 9 equals 0, when we go to try to solve that, it had no real solutions. So it turns out there's two 4th roots of 81 that are real numbers. So negative 3 and positive 3 are the real 4th roots of 81. All right, so it turns out there's a pattern here. There's some things that always will happen. So if n is even, so if n is even, so that would be, if you go back and look, that would be like x squared equals 25, so n was even. X to the 4th equals 81, n was even. If b is a positive number, so b would have to be a positive number. So again, if you go back and look, b is positive 25, so that would work. B is positive 81, that would work. But down here, you have a 2 where n is even, but 9 is negative. So this would not be what we're talking about. So we need an even n and a positive b. Then we get some notation here. So you have this little n with a little, what looks like a square root sign, but it's not always a square root, as we're going to see here in a second. So this little n with this symbol right here and the b under it, that denotes the principal or positive nth root of b. So if you see this little n with this symbol and a number under it, if that number is positive and this number right here is even, then that symbol, that notation, denotes the principal or positive nth root of b. If b is 0, so what if b is actually just 0, the number 0, then the nth root of 0 is just always equal to 0. Basically, if you have x to the n equals 0, then the only solution to that equation is 0. X equals 0 is the only solution. So then the nth root of 0 is 0. Well, if b is negative, then the nth root of b is not a real number. And the reason is x to the n equals b. There's no real numbers that solve that when b is negative. We just saw an example of that right here. So x squared equals -9. So that's an even n. So 2 is an even number. B is negative. And there are no numbers that when you square them come out to be -9. So that doesn't have any real solutions. So the nth root of a negative number, if n is even, is not a real number. Well, what if n is odd? So we saw an example of that too. So what if n is odd? So what if this n right here is an odd number, like x cubed equals 8? Well, when we did that one, we saw that there was one real, in this case, cube root, and it was +2 for that example. Turns out that always happens. So if n is odd, there's exactly one real nth root of that number b. Doesn't matter what b is. So if n is odd, it doesn't matter what b is. B could be positive, b could be negative, b could be 0. Doesn't matter. If n is odd, there's exactly one real nth root of that number. Well, there's some vocab that goes with this. So this notation where we have this little n, this symbol that looks like a square root symbol, but it turns out it's not always a square root. And then the number under it, b. Turns out this notation, that whole thing is called a radical. So when we say the word radical in mathematics, we're talking about this, where you have this little number up here, this little symbol right here, and a number under it. Well, that little n is called the index. So from now on, we'll call that the index. So this n right here is called the index. And this square root symbol doesn't always mean square root. It's actually called a radical sign. So up until now, you've used it for just square roots, but now we're going to start talking about different kinds of roots. So this is called a radical sign, and the number under it is called the radicand. Radicand. So I'm going to use that vocab from now on. All right, so let's look at some examples of this. So for A, this is something we're familiar with. This is a square root, because this is what you've been working with up until this point. And the way you know it's a square root is there is no little number, there is no index. When there is no index written there, it's understood to be a square root. So this is exactly the same thing as a little 2 with the radical sign, and then the radicand is 9. So if there is no if there is no index, it's 2. You don't have to write the 2. I'm just showing you that that's what it is. And then these work just like you're used to. So in this case, what this is asking us for is we want the principal. So what this is asking us for, this stands for the principal, which just basically means positive, square root of 9. So the principal square root of 9 is +3. But we need to make sure we understand something. This is asking us for the square root of 9. So that would be the same thing. Using our definition, that would be x squared equals 9. And that has two solutions, as we just saw when we solved one like this earlier. X equals negative 3 and x equals positive 3. However, when we write this notation, when we use the radical notation, we only want the principal or positive square root of 9. Well, since 9 had two square roots, negative 3 and positive 3, we want the positive 3. So that notation, we only want the positive square root. Let's look at B. B, we have negative principal square root of 9. So that's the same thing as negative 1 times the principal square root of 9. But we just, in part A, we now know what the principal square root of 9 is. It's 3. So we just want negative 1 times 3, and we get negative 3. Well, in C, we want the principal square root of 1/9. So again, we need to understand that this represents the principal or positive square root of 1/9. So the principal square root of a 9th is 1/3. And then how do we know that? Well, remember, to find a square root, you're just solving the equation, what number squared equals 1/9? Well, there's two numbers. X equals negative 1/3 and positive 1/3. So if I take negative 1/3 and square it, I get 1/9. So that's a square root of 1/9. If I take positive 1/3 and square it, I get 1/9. So that's a square root of 1/9. But this notation, when we use a radical, it represents the principal or positive square root. So it's the positive 1/3. All right, so let's try some cube roots. So notice now these are, the first two are cube roots, and then the third one is a fourth root. So let's do the cube roots first. So for a cube root, the cube root doesn't necessarily represent the positive root. So earlier we mentioned, so let's go back and look. Earlier we mentioned that if the index is odd, then there's only one real nth root of that number. So there is only one real number that you have to come up with. You don't have to choose between a positive and negative. There's only one real number. So for the cube root of negative 27, there's only one real number that when cubed is negative 27. So how are you supposed to figure this out? Well, remember, we're doing a cube root, so we want to know what number cubed is negative 27. And it only has one real solution. Give myself a little bit more room here. And that's x equals negative 3. So if I take negative 3 and I cube it, I get negative 27. So the cube root of negative 27, there's only one real number for that, and it's negative 3. So let's look at B. We want the cube root of a to the 9th. So same idea, even though it's not a specific number, I need to know what number cubed is a to the 9th. Well, if x was a cubed raised to the third power would be a to the ninth. So it must be a cubed. Remember, you're always just asking yourself the following question. What number cubed would give you the radicand? So what number cubed gives you negative 27? Well, negative 3 does. What number cubed gives you a to the ninth? Well, a cubed does. So now we have a fourth root, but it works the same way. You're just asking yourself the following question. What numbers, when raised to the fourth power, give you 81? Well, there's two real numbers that will do that. If you do x cubed, 3 to the fourth is 81, but also negative 3. So negative 3 to the fourth is 81. But remember, when this is an even number, when the index is even, this notation represents the principal or positive fourth root in this case. So we only want the positive one. So it'll be positive 3. We don't want the negative one. So when we use this notation, we want the positive nth root when n is even. When n is odd, you don't have to choose between them. There's only one real nth root when n is odd. All right. Let's try a fifth root. So now we have an odd index. This is odd. So there is only one number we're looking for here. So again, just remember, we're solving the following equation. What number to the fifth is 1 over 32? And it turns out there's only one number, and that's 1/2. So 1/2 times itself 5 times will give you 1 over 32. So this is 1/2. Well, for this next one, we have the sixth root of negative 1. Okay, so again, we're just solving this equation. What real numbers raised to the sixth power equal negative 1? Well, no matter what number you try, when you raise it to the sixth power, it'll never come out negative. Now we're talking about real numbers. So no matter what real number you try, when you raise it to the sixth power, it won't come out negative. So this has no real solutions. That just basically means there are no real numbers that solve that equation. So what's that mean for our sixth root of negative 1? It just tells us that this is not a real number. Turns out it's some kind of other number that we haven't talked about yet, but we will. So the sixth root of negative 1 is not a real number. So we can't come up with what it's equal to yet because we don't know what it's equal to yet, but we will soon. All right, so a few properties are going to come in handy, one of which we're going to use a lot, not just this year, but we're going to use a lot in the upcoming classes like pre-calculus. So the first property is if you have an nth root of a number, so n is the index, b is the radicand. If you have the nth root of a number b and you raise that entire radical to the power of n, now notice the exponent and the index are exactly the same thing. This is n and this is n. When you do that, it turns out the radical sign just disappears. So the nth root of b, all raised to the n, just turns out to be b itself. So the radical sign goes away. Well, this is going to be very similar, but notice there's a difference. Notice up here we have an index of n, and we have an exponent on the whole entire radical of n. For this next property, our index is n, and the exponent on the radicand, so the exponent on the number under the radical sign, is n. Well, it turns out if they're both the same number, that just simplifies to the radicand itself, b, but that's only true if n is an odd number. So if this is 3 and this is 3, this is 5, this is 5, 7, 7, 9, 9, 13, 13. If n is odd, then this whole thing will just simplify to b. That same thing will simplify to the absolute value of b if n is even. So if this is 2 and 2, 4 and 4, 6, 6, 22 and 22, it simplifies to the absolute value of b. Now this is one of the most misunderstood properties of radicals, and it's the most forgotten. People just don't remember the absolute value, but it's extremely important, especially as we move forward in math. So I'm going to harp on this the rest of this year, and if you have me in later courses, I'm going to harp on it then too. Okay, so the reason we need the absolute value is when we do an even root, remember this stands for the principal or positive nth root. So if this is even, then this notation represents the principal or positive nth root. Well, to make sure that we always come out with the positive one, we need the absolute value on it. So, and we did this a bunch earlier, we just didn't use absolute value. So right here, when we did these examples, we wanted the principal square root of 9. Well, there's two square roots of 9, negative 3 and positive 3. We chose positive 3. Now, we didn't use absolute value because we hadn't talked about that property yet. But technically, we could have done this example the following way, now that we know that property. You could have picked either one. You could say, well, the square root of 9 is negative 3 or positive 3. It's either one. But you just need to remember that it's the absolute value of that, and you end up with positive 3, just like we said earlier. So like no matter what you pick, you could have picked negative 3 or you could have picked positive 3, but it needs to be the absolute value. It needs to be the absolute value of that. Always, which when you throw absolute value on it, it'll come out to be positive. So this absolute value is a big deal. It's going to be a bigger deal when we're using variables instead of actual numbers. So once again, we could have done this particular example. So we have the square root of 9. Well, 9 is the same thing as 3 squared. So notice that n matches. We have an n here and an n here. Notice that n is even. So this is supposed to equal the absolute value of whatever b is. Okay, so in this case, b is positive 3, and the absolute value of positive 3 is positive 3, which is what we said the answer was. But it's also true, and this is why the absolute value is needed, it's also true that 9 is the same thing as negative 3 squared. That's still a true statement. Negative 3 squared is positive 9. So we have n and n. Notice they're both even and they're the same thing. So then, according to our property, this should be the absolute value of negative 3, and the absolute value of negative 3 is positive 3. So we get the same answer. So the absolute value guarantees we always get the same answer. Since we have two choices for how we could work it out, we still get the same answer no matter which choice we use. All right, so let's practice with those, and that'll finish this. So we have the square root of 15 all being squared. So that would be the same thing as, remember, we don't usually write the little 2 there, but we can. So notice that this n and this n are exactly the same thing. So that's this first property. So we have n, and they're the same thing. So that simplifies to just the radicand. So if you have a square root and you square it, it just comes out to be the radicand, 15. If you have a cube root and you cube it, it just comes out to be the radicand. If you have a fifth root of something to the fifth, so notice this n and this n are the same, but notice the exponent is on the radicand. Well, if you go back and look, That would be the second property, where this n and this n are the same thing, and if n is odd, you just get the radicand. Well, I guess that's not exactly true. So if these are both the same number and it's odd, you don't just get the radicand, you actually get the number that's being raised to the nth power. So the radicand would be b to the n, and you actually just get b. So you just get the base of that exponent. So we have a 5, which is an odd number, so you just get the base of the exponent, which is x. But on D, we have the square root of x squared. Now it's even, so we need the absolute value on it. So it's the absolute value of x. So that's that third property, where if these are the same number and they're even, you get the absolute value of whatever the base of that exponent is. And for this last one, we have the fourth root of y minus 1 all to the fourth. So notice it's even and they match. So I have a 4 and a 4. So I need the absolute value of the base of that exponent, which is y minus 1.